Good morning, everybody. My name is Anna Lindberg, and today my thesis partner, Rayne, Duff, and I will be presenting our thesis titled An Investigation into the Effect of Keel Rotation on Sailing Yacht Performance using a CFD-Based VPP. We would like to begin by thanking our advisor, Professor Onis, for his invaluable expertise over the past year. We would also like to thank our reader, Professor McMahon, and our editor, Professor Harris, for their thoughtful feedback on our thesis drafts. Finally, we would like to extend a heartfelt thank you to Britton Ward of FAR Yacht Design for providing us with data for the FAR 36. Sailors are constantly focused on finding new ways to improve the performance of their sailboat on a race course. While this can involve studying tactics or sail trim, the question we as naval architects often ask is, how far are they willing to go? To answer that, let's take a look at this video from the TP52 Super Series. This clip is taken at the end of the first upwind leg. Even after racing for an extended period of time, the sailboats are still within a boat length of each other as they round the top mark of the race course. With such close margins at this level of professional sailing, owners are motivated to find another way to gain that extra boat length. The best way to improve the performance of a sailboat on a race course is to increase its velocity made good, or VMG. The VMG of a sailboat is the component of its velocity in the true wind direction, which is ultimately the direction sailboats need to go on a race course. One way to increase VMG is by decreasing the leeway angle of the sailboat with keel rotation. The leeway angle is the difference between a sailboat's heading and direction of travel, and is essentially the angle of attack of the boat. When the sailboat moves through the water, its hull and appendages act at the leeway angle to create lift. By rotating the keel acts at a greater angle of attack, which can be described as the sum of the leeway angle and the keel rotation angle. At this angle, the keel contributes more lift to the hydrodynamic force balance. The lift provided by the hull and appendages must remain constant to maintain equilibrium, so the leeway angle will decrease to orient the hull at a smaller angle of attack. Consequently, the sailboat is better aligned with the flow of water, and its resistance is lowered. Because of this, the boat's velocity will increase, and with it, VMG. One sailboat was found to use keel rotation to successfully accomplish this effect. This is Rampant, a sailboat created by Roger Martin Design in 2004. Her keel is mounted on a rotating drum whose angle is controlled with a line in the cockpit. The design engineers claim Rampant outperforms her velocity predictions, but no information has been published regarding the impact of keel rotation on performance. This brings us to the objective of this thesis, which is to determine the effect of a rotating keel on the upwind performance of a sailboat using a computational fluid dynamics-based velocity prediction program. I will continue by discussing the theory before explaining the convergence study. I will then pass the presentation off to Rayne, who will describe the VPP workflow before discussing our results and conclusions before closing with recommendations for future work. Courtesy of FAR Yacht Design, the test vessel for this thesis was a FAR 36. This is a medium-sized sailboat raced in high-performance settings, which made it a suitable candidate for analysis. To evaluate the impact of keel rotation on its performance, we decided to create a VPP. To predict the performance of a sailboat, a VPP balances sail forces against hull forces until a state of equilibrium is identified. Like any steady-state dynamics problem, there are two conditions which must be satisfied. The sum of the forces is equal to 0, and the sum of the moments is equal to 0. Here are those two equations expanded to account for the most significant forces and moments in this problem. For the force equilibrium, this means that the thrust from the sails must equal the resistance from the hull and appendages. For the moment equilibrium, the heeling moment from the sails must equal the riding moment from the hull and the keel. When these two equations are balanced, the steady state boat speed, heel angle, and leeway angle can be identified. There are several popular methods for modeling the forces acting on a sailboat in a VPP. Choosing a method to calculate the hydrodynamic and aerodynamic forces largely depends on the computation time and required fidelity of the VPP. High fidelity VPPs will use fully viscous computational fluid dynamics, or CFD, to model hydrodynamic and aerodynamic forces. While these VPPs produce the most accurate results, the computation time is longer. In contrast, low fidelity VPPs will model hydrodynamic forces with systematic series and aerodynamic forces with sail force coefficients to characterize the effects of the mainsail and the jib. These VPPs are less accurate, but they have greatly reduced computation times. To create a VPP with minimized computation time and enough fidelity to resolve the small effects of keel rotation, it was decided to use CFD for the hydrodynamic forces and sail force coefficients for the aerodynamic forces. The sail force coefficients used today by the Offshore Racing Congress are based on coefficients developed by Hazen in 1980. For context, the ORC is an organization who creates ratings to handicap the performance of sailboats so that different sailboats can race fairly against each other. To do this, they developed a set of coefficients which could be used to predict the performance of any sailboat. These coefficients describe the lift and drag of each sail as functions of apparent wind angle, which is the angle of wind experienced by the sailboat. When sailing upwind, the apparent wind is stronger than the true wind because the speed of the boat adds an extra velocity component to the wind speed. In the graph shown above, these coefficients represent the lift and drag of a mainsail. While these coefficients may seem like they are specified at random intervals, these apparent wind angles actually represent typical points of sail encountered while racing. Using these coefficients, the lift and drag of any sail can be calculated using rho, the density of air, A, the area of the sail, and V, the apparent wind speed. These coefficients are the basis of the ORC velocity prediction model used to develop ratings for sailboats, and are what we will use to calculate the lift and drag of each sail in our VPP. To characterize the hydrodynamic forces acting on the sailboat, we chose to use CFD. But what really is CFD? CFD is a numerical simulation of a body in fluid flow. Using the Navier-Stokes equations to numerically solve for the behavior of complex fluid flow, we can calculate the forces acting on a body in a fluid, such as a sailboat sailing upwind. The Navier-Stokes equations are comprised of two governing equations, the continuity equation and the linear momentum equation. The continuity equation states that mass is conserved across the boundaries of a problem, meaning that mass is neither created nor destroyed. For incompressible flow, the continuity equation simplifies to this equation, because density is constant. The linear momentum equation states that momentum within the domain of the simulation is conserved over the course of the analysis. First, it is necessary to discuss the choice of turbulence model in our CFD simulation. As seen in the image on the right, there are three main ways to simulate turbulent flow in CFD, with the Reynolds to average Navier-Stokes, or RANCE model, large eddy simulation, or direct numerical simulation. As you can see, the level of refinement increases from RANCE to LES to DNS. RANCE is a time average solution which decomposes the velocities and pressures into a mean component and a fluctuating component to solve the continuity and linear momentum equations. We elected to use RANCE because it is computationally efficient compared to LES or DNS, and the refinement of the solution is acceptable for our analysis. RANCE is also the model of choice in other CFD-based VPPs. Before creating the VPP, it was necessary to complete a convergence study to develop the computational domain of the simulation. A convergence study is performed at the beginning of a CFD analysis to identify the optimal domain size, mesh density, and time step. Each parameter is changed while observing an output of the simulation, for example, resistance, as it approaches a single converged value. A trade-off must be made between increasingly accurate results and extensive computation times. The goal of the convergence study is to identify the computational domain which provides the best answer for the shortest computation time. The first parameter we iterated on was domain size. The domain size is the computational extents of the simulation. We followed the guidance of the International Tow Tank Conference on establishing a base domain size, which can be seen here. We then increased the domain size in all directions by 10% and 20% and monitored its effect on resistance. In this graph, the x-axis represents the forward extent of the domain non-dimensionalized by the LBP of the FAR36. The y-axis represents the resistance non-dimensionalized by the resistance from the corresponding simulation. As seen on the graph, an increase in domain size had a negligible impact on resistance. It was decided that this small increase in drag was not worth the increase in computational time associated with a larger domain. Thus, the final domain size was the domain proposed by the ITTC recommendations. Here we can see the final domain in 3 dimensions. The next parameter which was iterated on was mesh density. An essential part of setting up a CFD simulation is creating the mesh, where the computational domain is broken down into finite elements called cells. Each cell uses its inlet conditions to solve the Navier-Stokes equations and produce a set of outlet conditions. These outlet conditions are fed to the surrounding cells at each time step of the simulation. This image shows a cross-section of the volume mesh we developed at approximately midships. In areas of importance, the mesh must be refined to better capture the response of the fluid. For our simulation, we refined the free surface, the possible extents of boat movement, and the hull and the keel. Each of these local mesh refinements is defined as a percentage of a base mesh size. After completing the mesh convergence study, it was decided to use 0.08 meters as our base mesh size, which resulted in a cell count of approximately 6 million in the computational domain. The mesh convergence study was completed using a grid convergence index method, which ensured the base mesh size resulted in a solution within 3% of convergence. The final parameter iterated on was time step. The time step is the interval at which cells pass their computed outlet conditions to the next set of cells as inlet conditions. Smaller time steps lead to longer computation times, while longer time steps lead to shorter computation times. Within each time step, the solver will iterate several times on the solution to reduce the residuals, which are the difference between the solution expected from physics and the solution calculated by the solver. In the graph above, the x-axis represents iteration number and the y-axis represents the residuals. Note the logarithmic scale of the y-axis. In the red box, we see 1 time step worth of iterations. After completing the convergence study, it was decided to continue following the guidance of the International Tow Tank Conference and use 0.03 seconds for a time step. I will now pass the presentation off to Rayne to discuss the workflow of the velocity prediction program.
Thank you, Anna. Now that Anna has discussed the theory behind velocity prediction programs and how we developed our computational domain, I will discuss how we built our VPP and our results. We chose to use StarCCM+ for CFD because of its high level of customizability, which allowed us to directly integrate the Sailforce model into the simulation. Additionally, many modern VPPs use StarCCM as their platform of choice. In our VPP, an initial boat speed is estimated, and the sailboat is released into 4 degrees of freedom motion. Instead of allowing the sailboat to move in the forward or transverse directions, the boat is fixed such that it can only move vertically and rotate about its center of gravity. To help you visualize this concept, consider this boat in a tow tank. This boat is free to move in 2 degrees of freedom, but is not allowed to move forward or to the side. Here, the water speed is effectively the boat speed. This is the same approach we used in our simulation. To reduce the computational domain, we're creating a smaller domain where water enters at the speed of the sailboat, rather than a larger domain where the boat moves forward over the course of the simulation. For the purposes of our VPP, this means we cannot edit the speed of the sailboat during the simulation. Instead, we calculate the sail forces using empirical equations and allow StarCCM to apply the forces for one specific boat speed. For each time step in the simulation, the next orientation of the boat is calculated from the imbalance of forces. Eventually, a steady state will be reached, and it is possible to check if the boat is in equilibrium as defined by our VPP. If the sail forces are larger than the hull forces, the boat speed needs to increase. And if the sail forces are smaller than the hull forces, the boat speed needs to decrease. Because the setup of this VPP does not allow the boat speed to be changed during a simulation, multiple simulations are required to determine the final boat speed for each keel rotation angle. In StarCCM, there are several ways to model the motion of a boat. We used a popular motion module called dynamic fluid body interaction, which is typically used in marine resistance simulations. Within this module, there are several motion options which were applicable to the VPP. While we could have allowed the FAR36 to move freely, we chose to use the equilibrium mode. This mode locks the vessel at an orientation for a few seconds of simulated time before iteratively changing the orientation until the forces and moments in the active degrees of freedom are balanced. As we want to find an end condition where all the forces and moments are balanced, this was our best option. These iterative changes can be seen on this plot of heel angle as a function of time and are identified by the sharp jumps in orientation. While the equilibrium mode will find the position where the FAR36 is in equilibrium, it can only do so when the appropriate forces are applied to it. The sail force model is based on the ORC coefficients, and from the front view, we only see the portion of the force heeling the boat. In reality, the sail force heels the boat and also drives it forward. So the resultant looks more like this. But for our purposes, let's consider the driving portion of the sail force. Here, the sail force is offset to the starboard side of the boat because the boat is heeling. This applies a turning moment to the boat in the opposite direction of the heel. To counter this, the rudder needs to apply a turning moment in the opposite direction. When the rudder applies this turning moment, it also causes a side force. The equilibrium motion mode finds a position where all the forces and moments will sum to zero, but it only does so in the directions the boat is free to move. The boat is not free to move in the transverse direction. So ensuring the sum of forces in the transverse direction is zero has to be done another way. Thus, the rudder force is defined such that it always ensures the sum of forces in the transverse direction is equal to zero. This means the rudder force is always equal to the side force of the sails minus the transverse force from the hull and keel. It does not replace the lift from the keel, but simply closes the problem. This way, the equilibrium motion mode will find the position which makes the moment from that rudder force equal to the turning moment from the sails. This method of modeling the rudder force is much simpler than what is done in some other VPPs and allows this VPP to work correctly within its parameters to find equilibrium. Now, let's look at it in action. I promise this isn't actually how a sailboat moves. After a short period where the water is allowed to come up to speed, the equilibrium mode starts to change the position of the FAR 36. First, it trims it forward, and then it heels dramatically before eventually finding a steady state condition where the boat is in equilibrium. The colors on the water indicate the elevation of the free surface, with red representing crests in the wake and blue representing troughs. Each of these simulations took about 3 days to produce approximately 100 seconds of simulated time. For each keel rotation angle, 5 of these simulations were completed to identify a boat speed where hull resistance is equal to sail driving force. This was the test matrix, which the VPP was used to complete. Notice that the first iteration always starts at the same boat speed, because at that point in time, we do not know what the final boat speed will be. For this study, we chose to test the FAR 36 in 10 knots of wind at 39 degrees of true wind angle, after looking at the output from FAR Yacht Design's VPP. This was because 10 knots was the highest wind speed before the boat became overpowered and the aerodynamic force analysis increased in complexity. Also, at that wind speed, a true wind angle of 39 degrees had the best VMG result, making it a good starting point for this analysis. 4 keel rotation angles were chosen: 0, 1.5, 3, and 4.5 degrees. These angles were chosen because they were estimated to decrease the leeway angle to near zero at the higher keel rotation angles. After a few iterations, the final boat speeds can be identified for each keel rotation angle. During the early iterations, the driving force of the sails and the resistance are not expected to be equal. This graph shows them plotted together so they can easily be compared at the end of a run. Here, the time is on the x-axis and the value of each force in newtons is on the y-axis. This plot is an example of an early run where the forces are not equal. Notice that the resistance fluctuates, but after a while, it oscillates consistently around an average value. The average value of resistance in this case is slightly higher than the sail driving force at the end of the run. This means the speed of the boat needs to be decreased in the next simulation so that the resistance will decrease slightly. This graph is the same as the previous, but shows a new simulation where the speed was slightly lowered. Now the resistance is oscillating around the driving force of the sails, meaning the boat is fully in equilibrium. And this speed is the final velocity prediction for this keel rotation angle. The iteration process was completed for every keel rotation angle. The final velocity predictions are found at the bottom of this table, and we can see that the values are slightly different for each iteration. Now we can look into the results in more detail. This graph shows the relationship between keel rotation angle alpha on the x-axis and leeway angle theta on the y-axis. As keel rotation angle increases, leeway angle in the simulation decreases with an approximately linear trend. Note that when the keel rotation angle is at 4.5 degrees, the leeway angle is near zero, which means the hull is almost completely aligned in the direction of travel. Based on this graph, we should expect to see higher predicted speeds for higher keel rotation angles. This graph is the key result of the investigation. The x-axis again shows keel rotation angle alpha in degrees, while the y-axis now shows a non-dimensional representation of VMG. The VMG is non-dimensionalized using the base VMG predicted at 0 degrees of keel rotation to easily show the difference between the results. The notable trend here is that keel rotation slightly improved VMG, which was what we predicted should occur. The most significant performance gains occurred at 3 degrees of keel rotation. After 3 degrees, additional keel rotation does not provide further benefit, but is still better than none at all. So what does this mean? The best results were observed for a keel rotation angle of 3 degrees, and the VMG increased by over 0.5%. This is a bit of a vague conclusion, so let's give it a physical interpretation. For a 15-minute upwind leg, a FAR 36 with a keel rotated to 3 degrees would gain 1 boat length over a FAR 36 with no keel rotation. While this impact is somewhat small, sailboat racers are always looking for ways to gain distance, and 1 boat length can be the difference that results in a win. That being said, 15-minute upwind is quite long, and there are many other factors that could happen in that time which would make a larger difference than 1 boat length. Ultimately, the results demonstrated that keel rotation has a small positive impact on upwind performance. However, the gain is quite small, so modifying an existing vessel to install a rotating keel is not recommended. The price of such a modification would be quite high, and there are likely other places that money could go to make the boat faster for less. It is also important to mention that installing a rotating keel could result in a rating penalty in some handicap rating systems, which would negate all the benefits to performance. For future work, the immediate continuation of this thesis could be to keep testing more keel rotation angles, and wind speeds. A broader expansion of this thesis could use the sail force model we integrated to create a 6-degree of freedom VPP, which requires a new rudder force model. This VPP could also be used to investigate the effect of different modifications to the boat we tested, or even to test entirely different boats. The possibilities are very open, and VPPs can be used for anything that requires the prediction of a sailboat's speed. Thank you for listening to our presentation. I would now like to invite David, Ben, and Anna to the stage to answer any questions.